the amount of billions of triples. So that is creating really a great opportunity for creating some kind of innovative web-based services using this linked data. But in order to use this kind of data, the first thing we need to deal with is to have some kind of universal organization of the products, because we all have that kind of experience. When you come to an e-commerce website like Amazon or eBay, you often need to browse their product categorization. That helps you to navigate through the website to find the products you want. And that is for a single website. You think about millions of products on the internet coming from hundreds of thousands of different websites. Now, obviously, this universal representation of a product taxonomy is even more important. So we have already linked data in the products. Can we use that information directly? The answer, unfortunately, is no. First of all, these linked product data is very shallow. The usage of the schema.org in product data is very shallow. We're looking at about only 6% of products that actually has the category information. And let's call this website-specific product categorization labels or site-specific product labels, just to avoid confusion later on. The second problem here is that the labels that are used across different websites are highly inconsistent. If you look at examples down here, these are taken from different websites that are selling some kind of shirt. So as you can see, it's very difficult to use them directly. And that means we need some kind of automated methods that help us to classify products according to some kind of universal categorization system. And that's the task we're looking for today. So actually, it's a lot of work's been done in this area. Product classification typically is treated as a test classification task because we're looking at assigning labels, classes to products based on their metadata, their attributes, which are often textual data as well. A slight difference is that we have to assign labels coming from certain hierarchies. So this is the Google product taxonomy. So we're looking at perhaps assigning a label from this level here and another label from here and there and there. So that's the task. So we said that the classification is done based on the metadata that is associated with products. Looking at what kind of metadata is being used in the literature, very often names, because almost every product will have name. When there's some descriptions that are available for the products, they are also used. Some researchers have also gone an extra mile in order to get more structured data about a product. So they build, for example, lighting information extraction processes that try to parse product specifications and use that information as features or metadata. In terms of algorithms, because we're talking about text classification, so any machine learning algorithm, can be used for this task. And obviously, deep neural nets find its place here because it's getting more and more popular. And we're looking particularly in this talk a structure called Deep Categorization Network, DeepCN. And that's because that is the model which our work extends. So I'll cover that with a bit more details in the next slide. What's the limitations? Well, first of all, if you look at state of art, typically they are looking at assigning the labels to products coming from a single website. The tasks we're looking at here are products coming from hundreds or even thousands of websites. And when you deal with products coming from these heterogeneous sources, you're looking at a higher degree of inconsistency. All this work so far has not used site-specific labels, so that are the categories that's being assigned on the individual website. As we said, these are very inconsistent. I mean, that's understandable because if your task is about assigning labels to products from a single website, well, your goal is really just assign the site-specific category label, so you can't use that as an information. But if you're looking at classifying products coming from different sources into a universal taxonomy, then the site-specific labels could be useful. So we talked about DeepCN. Now, that model there, the idea is that you use several different RNN models And each RNN will take one particular input of metadata, and you learn features from that source, and you concatenate all of them together and fit into the final layers for classification. So we asked the question, well, can we generalize that? RNN can be used. What about using CN? What about using hierarchical attention network? So we want to try all these different substructures and see if there's any difference in terms of performance. So we have these questions, and that is the question we want to answer with this particular piece of work. We're moving on to methodology now. So this is the diagram illustration of our model. So as we said, it's based on the deep CN network. We call this one as the generalized deep CN. That's why GEN should be capital C there. Apologize for that. So we made some small adaptations. Let me just go through this quickly. First of all, we use an embedding layer where we just take pre-trained word embeddings, the globe word embedding vectors, whereas in the original work they use one-hot encoding, so the embeddings learned from the data. Second, the second difference is the sub-DN structures. As we said, originally the authors used RNN. Here we try to compare CN, LSTM, and hierarchical attention network. The third difference is the hidden layer, where originally there are two layers, but empirically there's no much difference in the results reported by the original author, so we just use one hidden layer instead of two. So in terms of metadata, we try 3 different types, and we kind of mix them up in different combinations. There's product name, description, and we also said that we use site-specific product labels. And we have 3 different ways of using the information, because we want to understand the extent to which we have noise in this kind of metadata, and also whether that affects on our learning. So 3 ways of using site-specific product labels or site-specific product categories. The first one, we just use some shallow processing, so some very simple normalization, lowercasing, lemmatization, etc. The second one is we cluster these labels. So the idea is that if these labels look all similar, well, if we try to cluster them, we should be able to group them together in a single group. And we can use that cluster membership as feature instead. The third one is what we call cleaned labels. So this can look fairly complex, but let me just go through that because it's not that complicated. So we take a site-specific product label. As an example, you have hardware, hardware accessories, cabinet hardware. We break it down into 3 parts based on a separator here. And what we want to do is we want to pick one most informative part from these. The way we do it, well, we firstly get rid of any parent labels that are not very informative. So if they are all capitalized letters, or if they're repeated at different levels. We also remove stop words and use some patterns to remove some content as well. So, sales or the price range. Then we want to select just one part of it, that is the most informative one. So first, we try to compute the TF-IDF of all the words in the remaining processed label parts. And then we calculate a score for each part based on the average TF-IDF of its composing words. And we just take the highest scoring part. So simple as that. So, for example, perhaps given that particular product label found on one website, we will just get cabinet hardware. Just an example. Okay, so on to the experiment. We used a previously published data set, and this contains just over 3,000 product instances from 700 websites. They're annotated using the GS1 Global Product Classification System. This has more than 3 levels of classification, but in this gold standard, we only have 3-level annotations. Level 1, there are 37 classes. Level 2, 76. Level 3, 289. So we're looking at 3 tasks here, really. We create different model configurations. So we try different metadata separately, name, description, site-specific product label. We try to combine them, name plus description, name plus the site-specific label, and so on. As we said, we also try the kind of pre-processed site-specific product label. So it could be label cluster or cleaned labels. Skip that. Okay, so on to the results. So I just want to see that on this slide, we're only showing the macro F1, but there's the same patterns in the accuracy as well. We only show cluster with a size of a number of 50 clusters because that's the best result we can get. First of all, the best results is obtained when we have used all the metadata. So if you have the metadata available in your data set, let's use them all. And I think what's really surprising is that when we're looking at the separate metadata, the best one is just using site-specific categories. And you can see the results are much better compared against name or description. So it's interesting because although we know that the product label, site-specific labels are highly inconsistent, this clearly tells us that they do tell us something interesting, useful about how to classify products. And if we're looking at the way we try to clean them, unfortunately and surprisingly, they don't really work. We've done some analysis to understand why. First of all, clustering, it turns out that we end up with a lot of large clusters. So most products get stuck within just a handful of clusters. So obviously, clustering isn't very discriminative. And in terms of cleaning, what we found out is that although we can manage to get some reasonable labels, but perhaps the way we try to choose one most informative part of the label is probably too aggressive as a strategy. Because we're losing a lot of useful information that can be coming from other contexts like tools and hardware, because in this case, we only got chisels. And if you're interested in how do we compare against the state of the art, so this is just one slide to summarize that. You want to compare this row against 17 and this row against 16 because they all use the same set of metadata. But as you can see, our method works better, particularly on level 2 and level 3. And I think that is a very good advantage because those are where the task can be harder because we're dealing with a larger amount of classes. Okay, I think I'm running out of time, so I'm going to just leave it here on the slides and answer your questions.
Okay, thank you. Questions? I imagine the product categories or labels follow a long tail distribution. So did you study, if that is the case, did you study whether your predictions were more accurate than at the head of the tail or head of the distribution or the tail of the distribution?
I'm not entirely sure I understand the question. We didn't really analyze the distribution of the categories, though. So I'm not entirely sure whether that has certain impact on our relation with the accuracy.
Any other questions? So I could have a quick one. So you said that the cleanup version is actually not working as good as. So what kind of inconsistency are there across these site-specific labels?
There are quite a wide range of inconsistencies. So there are cases where normally you would expect, if you look at a particular category path, you would expect probably the path will become more specific from left to right, but there are a lot of cases where it's actually the other way around. There are also a lot of situations where the actual most informative part is probably not at, people would imagine might be at the end or in the front, or maybe the word that is quite unique inside that path. Can't think of a good example. But sometimes it is words that are more general that makes more sense.
Okay.
So I can show you some examples if you're interested offline, but I can't think of one on top of my head.
Okay, thanks. Any other questions? If not, let's send the speaker.
Thank you.
So good afternoon, everyone, and my name is Yoon Chan, and I'm a joint PhD student from Southeast University and Monash University. And I'm very appreciative today that I could have a chance to stand here to share our work. And our work is about difficulty controllable multi-hop question generation from knowledge graphs. So this is the work that cooperated with ISWC, Yuan Fang, Ganesh, Guilin, and Lian Li. And ISWC is the first author of our work. And I will categorize our presentation into 5 parts today. And first of all, as we all know that knowledge answering over knowledge graphs, a question answering over knowledge graphs, which is KBQA, is intense research focus nowadays. And it's a very useful method that to transform the natural language questions into the structured queries to help the user to retrieve the entities that they want. So we could categorize the KBQA into simple questions, multi-hop questions, and more complex questions. This kind of more complex questions is to reasoning based on the different triples in the knowledge graph. So we have many models that could be have been proposed these days, but all of these models, most of these models are based on the neural network. And as we all know, if we want to train a neural network to work as we expect it, we need to feed them with a huge amount of data, so that we'll have a problem that if we don't have the sufficient data, what can we do to train these models? So, as we mentioned, that the limited availability of data set is a hinder here to train the models. So we have some data set nowadays, and we have some single hop questions. The amount of these single hop questions is really large, but it is only a single hop question. It's the simple questions, but not the complex questions. And we have some data set for the multi-hop questions. For example, LC quad, complex web questions, web question SP, and PES questions. But all of these questions, the size of these questions may be around a few thousand, so it is hard to train a deep learning model. And also, we have a complex question data set, which is CSQA. But this kind of data set is established based on some predefined templates, so we could not ultimately to create the data set. So there's a challenge here. It's limited in size, so we don't have enough data set, and all the data set created for QA, especially the multi-hop complex questions, are manually created or semi-manually created, which is we need to collect templates, and based on the templates, we could establish to create the questions. So here is some typical sample of the multi-hop questions. The first one is we need to use a sequence of triples to solve a problem. For example, here we need to know who is the Henry I. Duke of Guise's mom, and who is her spouse. Obviously, it is his father. So minimally, so we need to know who is Henry I. Duke's father, and then we need to know who is what is his name. So we need minimum 2 triplets to solve this problem. And the next sample is a star format sample, which is that we have a root entity, which is Norway, but we have many same relations that linked with this root. The relation is the official language. So in this problem, we need to count how many languages or what the languages are to spoken in Norway. So these are 2 typical samples of multi-hop questions. And our contributions is to use automated function to automatically create this kind of multi-hop questions. And we use the answer encoding to update our model, and we use difficulty embedding or difficulty estimation to estimate how difficult the question is. And our technique could generate the questions of the high quality, and we share our data sets and code here. So we have some QA models, for example. They could solve the simple or multi-hop or complex questions, but most of these models need a huge amount of data set to train because it's a neural network models. And also we have some QG, which is question generation over KG. We have some QG models, but most of these models are based on the templates, and we have some neural network-based model to generate questions, but it is about a single triple questions, which is simple questions. And we have some models could generate the questions from the text, but the information source here is changed from the text to the knowledge graph. So here's our model. Our model actually is a graph-to-sequence model. Why we call it a graph-to-sequence model? Because in this model, the input is not a sequence of data. It is a graph, you know. Graph is not a sequence, so we can't regard it as a sequence-to-sequence model. But we use some method to try to embed, try to encode this graph. And suppose we have a subgraph of the facts. We have n facts, and we need to take this n facts as the input, and also we take the original questions as the training, as the supervision signals to train our model. So actually, the objective of our model is to try to find the most appropriate distribution probability of the words in the output vocabulary. So this is our model. Our model is a transformer-based model. So we have some difficulty estimation, answer encoding here to try to update the model. And here is for encoding. Encoding is a typical transformer encoding model here, but we use some tricks here. And firstly, it is the answer embedding, which is that we have triples. We have a subgraph, and in this subgraph, we have multiple triples. But in these triples, some entities are answer, but some entities are not answer. So we need to find a way to distinguish these answer entities with the non-answer entities. So we use a linear layer here to try to embedding this kind of one-hot vector into the model-sized vector. Why we use this one-hot vector, which is that we use this one-hot vector to distinguish whether this entity is answer or not. And when we got this kind of mark, we could embed this mark into a vector, and we sum this vector with the input embedding and to form our input embeddings. And after we have input embeddings, we could use the transformer to try to encode this embedding. And this is how our encoder works. And next thing is that how we estimate the difficulty, or how we encode the difficulty here. We have two metrics. One is confidence, and another is selectivity. The confidence is about that if the mentions in the question are easy to link to the entities in the KG, so we think that this kind of mention have higher confidence, which means if this kind of mention have higher NYAM score, then we think that this kind of mention have higher confidence. And the selectivity is that suppose we have two names of entities in the KG. One name is John Smith, you know. There are many John Smiths in the world. We can't recognize or distinguish this John Smith with another John Smith. But if we try to find who is Elon Musk, I think there's only one Elon Musk in the world, so it is easier to distinguish it. So we think that if the selectivity is lower, then the question is more confusing, and it is harder to solve this kind of question. So our metric is that if the confidence is higher, the question is easier to ask. If the selectivity is lower, and this question is harder to ask. So that's how we estimate the difficulty. Then after we estimate the difficulty, we have a threshold. If the value is under the threshold, we think that it is an easy question. If it's higher, we think that it is a hard question. And we could distinguish the questions into two parts, two groups. One is the easy and another is hard, so we use a one hot vector to represent this easy and hard. And after that, we embedding these kind of one hot vectors to the output embedding. Then after we have the output embedding based on the typical transformer operation, we could get the output. The output is the predicted questions, and the loss is the blue or the rogue error, something like this. We could use this log. We could use the loss is the cross entropy loss. Sorry, the loss is cross entropy loss. We could use this loss to train our model. So that's the end of our model, and these are data sets. We try to use the data sets, the questions that in these three kind of data sets, and the training signals here is the subgraph and the questions. We use the subgraph and the questions as a pair to train our model. Suppose we have the subgraph, we transform this subgraph into an embedding, into a vector. And we use the original questions as the supervision signals of the decoder to try to train our model. So we use these three data sets to train our model. And we have some baseline methods here. The baseline method here is L2A. L2A is LSTM-based sequence-to-sequence model. Because it is a sequence-to-sequence model, so we need to try to transform the graphs into a sequence of triples to make the input change into a sequence, and then we could run this sequence-to-sequence model, which is L2A, which is proposed as L2A. So L2A is a state-of-the-art QG model, but it is generate the questions from the text. We are generating the questions from the knowledge graph, so the information source are different. And we used some automatic evaluation. We have some metrics to automatically evaluate our model based on the blue, rogue error, and meteor. And also we have some manual evaluation, which means that we have some participants, we have some volunteers, and they could manually evaluate how correct these questions is, and what's the quality of the syntax, what's the quality of the semantics and of this question, and whether the difficulty level of this output question is the same as we expected. For example, we input the easy, we input the we input the hard difficulty level into this model, but the model outputs some easy questions, so we think that it is a not good output, it is a not good generated question. And here is some statistics. We could find that in all these two data sets and for all these three different metrics, our model have the state-of-the-art results. And AE here is about answer encoding. If we remove the answer encoding from our model, we could find that our model will be impaired, the performance of our model will be impaired. So it could be found that AE, or we call answer encoding, is important here in our model. And this is the manual evaluation, which means that the percentage of the questions that we generate is good, and the percentage and the number in the parentheses is about that the agreements with the participants. So it could be found that our model still have the state-of-the-art result. And here's some example. For example, we have the same knowledge graph, sub-knowledge graph, but we have different difficulty level, and we could form different questions we could find that the harder one is obviously more difficult than the easy one. And this is how we use the 3 different models to generate the questions. We could find that MHQG plus AE, which is the best model, could generate the question with the highest quality, and it is the most fluent. And here's another sample that how our model generated the questions from the subgraph and the different models. So we propose a novel transformer-based model for generating multi-hop questions from subgraphs. We try to solve the challenge that the input is graph but not a sequence, how we use the sequence-to-sequence model to solve this problem. And also we use the difficulty modeling, the answer encoding to try to update our model. And the future work is that we could generate even more complex questions, or we could take the structure of the subgraph into account to try to estimate the difficulty, but not just the ambiguity of the mentions in our questions or the knowledge graph. And also we want to try to combine QA and QG into a same dual task, and we want to try to solve these 2 tasks simultaneously. And that's the end of my presentation. Thank you very much.
Thank you.
Yeah, thank you.
Any questions? I've got a few. So it's very interesting work. I mean, obviously, if you want to properly do this generation, you need to kind of have a classification of different kind of difficulties. So what are the key dimensions in your framework for the difficult questions?
Difficult questions here. Yeah. We have, when training and testing, we have 2 methods to try to control this difficulty level. And when training, the difficulty level here is based on the ambiguity of the mentions in the questions and the knowledge graph. Suppose that we have mentioned Turkey here in our questions, but you don't know whether this Turkey is about a chicken or about a country. So if this kind of mention could, if we have many of these kind of ambiguous mentions in our questions, so we think that it is hard to answer this question because we need many different irrelevant triples to try to solve this problem. So we think this kind of question is more difficult. That's how we estimate our difficulty in our work.
Yeah, well, one observation obviously is that you model the problem as graph to sequence.
Yeah.
But sometimes some of the difficulty of the questions are not necessarily from the graph, but it's well known that if you have negation in your question, it will be quite a bit harder than those without negation. And there are other things that you could actually appear in the question, but not necessarily from the graph.
Yeah.
So do you have any thoughts about that?
Yeah. So we have mentioned that we have a manual estimation of this question. So besides of this kind of ambiguity of the entity dimensions, also some volunteers or we have some manual work to estimate the question based on how hard it could be reason between these different triples and how complex the question is, and we have this manual estimation. And also we could we use this kind of manual evaluation of difficulty level as the training signal and try to encoding it into our work. So actually the difficulty level here is combined by 2 things. One is the how complex the knowledge graph is, and another is how hard this kind of question is.
So obviously, I think in your presentation, there are at least 2 angles, right? One is question understanding. The other part is kind of question reasoning. So in the generation, so what is the balance between the 2? Is it kind of more focused on the reasoning side or more focused on the understanding side?
Currently, we focus more on the ambiguity of the entity dimension. And in future work, we will try to focus more on another thing.
Okay. Any other questions? If not, maybe I could ask the last one as well. So L2A, right? I mean, obviously, as you said, it is sequence to sequence. But, you know, in the graph, we don't have order for the nodes, for the entities.
Yeah.
So is it fair to use L2A as baseline? I mean, or have you done anything not trivial to actually properly use L2A?
Yeah. Actually, how we use L2A is similar to ours, but it can't be the same as ours. And we try to, when we try to compare with their works, and we try to put the triples in a sequence, and this sequence is at some extent related to the questions. For example, that the examples that I mentioned before, we need to first find a person's father, and then we need to find his father's name. So we put the triples here. The first triple is about the person's father, and the next triple is about the name of this person. So we try to put this kind of triples in order and try to regard it as a sequence of triples. So we did some work to try to compare our work with L2A in a fair way.
Okay,
yeah.
Thank you.
Yeah, thank you.
How you do these things on a PC.
I think maybe it's this guy.
There you go. Oops.
So if we minimize that, maybe it's open already. Yeah. Don't save.
Okay, that's a little different.
Yeah, yours keep PowerPoint, right?
There we are.
Yeah.
Okay, good.
Okay, we have the third presentation today from Jim to talk about deep learning for noise-tolerant RDF reasoning.
So I learned a new phrase the other day, which was PowerPoint karaoke, which is where you must give the talk from someone else's slides. And I'm today going to practice what is a bit of PowerPoint karaoke because we discovered on Friday that the first author of the paper did not get his visa after having been told repeatedly that it would be coming. And so I am presenting a presentation that was basically sent to me on yesterday night. But this was one of my PhD students. I have worked on it, so I do know something about the work. And so I'm going to talk about what we've been doing. I'm going to give a little bit of motivation of my own before I get into the motivation specifically in the paper. This is a journal track paper, so the actual paper was in the Semantic Web Journal, special issue on semantic deep learning, and all of the code, the models, and the data sets are available online at that GitHub. And the first author is Basim Makni, who, again, is not here because of the visa issue, and is the one who really should be presenting this work because he was the one responsible for most of it. So we're going to talk a little bit about knowledge and learning, what kind of embedding we were doing, what sort of ground truthing, the embedding model we use, which is a little different than what you've heard in the past two talks, and a little bit about results, not surprisingly. But the motivating thing for a lot of the work in my lab now is really starting to look at knowledge meets the stuff coming out of modern AI. When you start looking at the perception world, right, the text world, there are now a lot of very powerful things coming along where those of us in the AI community have for many years said, in the KR community have said, you know, when the vision systems get good enough, then we'll worry about it. Till then, we're just going to use these nice logic representations. Well, guess what? The vision systems have gotten good enough, and what they're producing don't really look like a lot of the traditional logic representations. The question is, how do we start putting these together? there's been a sequence of 3 or 4 different PhD theses from my lab that have looked at some of this. Bassem was the first. But essentially, so the way I like to motivate this, and this is part of a much, much longer talk, you can find my slides online, is if we look at a picture like this and said, what's the relationship between this man and this woman, you get something. And I could show you if I had time what, scene graph labelers and things like that do. But if I make this change, right, so I just open up the aperture a little, and you can now see that in the background there's this woman in a white dress, that actually changes the context pretty drastically. Now most people knowing the U.S. Wedding sort of culture would say, oh, that's a wedding. Now you would start making hypotheses. Maybe that's the groom dancing with his mother, right? In fact, that in some informal testing in classrooms tends to come up a lot. Okay? But I could keep adding information. And so at some point, sooner or later, you reach the point where you could just say, just increasing the size of the training set. So you say, now you give me wedding pictures. Now you give me this pictures. Now you give me that pictures. Okay. I come from New York State. In New York State, we allow gay marriage, right? So if the 2 people getting married are both women, then that's not the groom dancing with the bride. That might be one of the 2 getting married dancing with a different relative, et cetera, et cetera. So we can always keep adding complexities, right? So that's been motivating a lot of the thinking in my lab, and we're actually looking at a lot of it in more technical type areas. So, for example, in these 2 pictures, the kind of context switch is happening in the same way it was in the previous, and the kind of exceptions are there. And I won't go into details except to say that picture A, most image analysts and most deep learning systems will say there is a tumor there when it turns out there's not a tumor there, but you need the medical record to know the reason the tumor is not there is the person has had a mastectomy, so there can't be a tumor there, right? So that's that exception case. Okay, the other one is a very rare kind of cancer that's very hard to detect, or a rare kind of positioning of a tumor. And again, unless you had a training set with lots and lots of these in it, right, you're not going to see it. But if you took 1 million cancer patients, maybe one of them would have this. So again, you need knowledge of the medical situation to be able to do some of these more complicated cases. Okay, which is a long way from the actual paper we're on, but it just is sort of the motivation. So what Bassem proposed to me, and I figured he had no way it was going to make it work, was that he would be able to use some reasoning. He would be able to train up a reasoner in RDF, an RDF reasoner using deep learning techniques. But that wasn't that hard. It took some interesting technical tricks, but the hard part was, so what? Right? What was interesting about the knowledge representation issue, because we have plenty of deep learning, deep logic systems, description logic systems that can get the correct answers, right? But when you started looking at noisy data, so for example, if you take dbpedia or Freebase or any of those, and you actually apply all the rules to get a deductive closure, you get a lot of garbage, because every wrong inference, every wrong assertion, right, every inconsistent assertion gets propagated through all of the reasoning you can do about that. So the question that started to come out is, in theory, the deep learning systems are better at recognizing exception cases, at recognizing categories and things like that. So the question is, could we train on inferences in such a way that the systems would be able to actually do the inferencing, but also recognize when something didn't look right. So the overall graph doesn't make sense with certain inferences. It makes more sense with others in terms of other graphs you've seen. So this goes back to something I've been saying for many, many years, that what motivated a lot of the semantic web work back in the late 90s into the early 2000s was exactly that the web is noisy, right? Text extraction, right? A really, really good text extraction system might have a F1 metric of 0.93, which means 7% of the stuff is junk, not exactly, but close enough, right? So in other words, there's a lot of errors in there. You just don't know what they are, things like that. So the question is, when we look at some of the things going on the web, can we find can a deep learning system do better than a traditional reasoner at recognizing the situations where there's something wrong? So just as an example, in DBpedia, turns out there are a bunch of things that are both people and places. Okay, in fact, and of course, if you have something that's both a person and place, then the place, if the place was the correct inference, the inference off a person is that that's an agent, right? But a place can't be an agent. So essentially, you can find a lot of these. So just this one example of things that are both people and places, you find at the time that we did this, 1,716 of them in DBpedia, right? So again, these are things where any decent reasoner will make an inference that is incorrect because at least one of these two statements must be incorrect in the real world. Okay, just a thing. So what Bassam's thesis work was to look at noise handling structures. How did we really look at some other things? And then how do we do graph embedding for this? And he compared, in the actual journal paper, a lot of comparisons that you can read about. But essentially the question is, can we find an adaptive way of getting rid of the noise rather than doing the cleaning by hand for these things? So the other thing is when we look at most graph embedding techniques, right, most graph-to-graph learners, right, are not good at learning a graph which either adds or deletes information from the previous graph rather than just manipulates the graph. Or you end up with two graphs turned into vectors that you can do vector math on that may or may not actually have much to do with the actual inference space. So after a lot of work trying to use many of the graph-to-graph deep learning systems, eventually we came up with something quite different because basically most of these embedding technologies were not designed for RDFS. The other thing is one of the things that we want to be looking at is things that are higher up in the hierarchy, right? So if you're a person, there's an inference about things that you do as a person. If you're a place, there's an inference about things you do as a place, both up and down. So again, that propagation is complicated. So the overall approach that was used in Bassam's work is essentially you take a graph, right? So this would be, typically your assertion graph in RDF plus the ontology. You can run any of your favorite reasoners. He did it through Jenna. So Jenna will generate a new graph with at least one new triple in it, right? Use the same encoding to create the graphs without the inference and the graph with the inference. You say, okay, so this is an inference being made in this graph. We turn it into a set of tensors, which I'll show you very briefly because the details are in the paper and are in the doctoral thesis. And being the advisor, I won't claim that I know all the details. That goes into a sequence-to-sequence learners where we can then do the actual comparison, training, and evaluation. So essentially, we're turning the graphs into a set of tensors, using those tensors into a sequence. So it has a lot of similarity to the last paper with the exception that we're not doing the embedding per se. We're not doing any of the embedding kind of maths. For ground truthing, then what you can do for the cases where you actually know all of the things, we can actually take a particular set of facts. We can say what should be done by a rule-based system. Did we actually learn what was supposed to be done? And so we can compare to something like a Jenna reasoner or something like that. So the work was done against two different data sets in the paper. It's actually been tested on more than that. One was an artificial data set. So we took Lubum. We proved we could learn Lubum up to a fairly good level of accuracy, and then added noise, which I'll talk about in a minute, and did the usual train, validate, and test. The other thing that was run in evaluation was actually to generate from DBpedia what was called the scientist data set, which is not just the scientist. It's essentially what we would call the RDFS closure of all of the people who were asserted to be scientists. It comes up with a lot of weird stuff. So if a scientist was born in London and we have facts about London, it will be in there. So it's essentially propagating a lot of facts about it and generates a very large graph. So again, we look at it places, things like that, that are related to the scientists. Now, the biggest question is how to embed this. So this was really where the doctoral thesis work that led to the journal paper. And the key thing was finding a mechanism to turn an RDF graph into a set of things which can be compared and then learned. So essentially, the idea is that you're using a tensor representation. I don't really have time to go into it. It turns out that if you use this representation, you have potentially a very large number of items if you do the whole cross product. But if you actually look at how to lay things out as this, what's happening is what you're really doing is you're taking all of the terms, all of the software version, organization, advisor, et cetera. You have the entities in one thing, and then you have the related properties in the other. So I can assert in each of those matrices, there's a 1 in there somewhere which says that represents this person as this advisor, right? And then you turn those sets of those graphs, those tensors, into sequences, and so you end up with this sequence of words. So essentially, RDFS reasoning becomes figuring out which sequences are legal, which, given given the graph, you get a second graph out, which is the graph plus the legal inference, plus the inferences that the system has learned. Details, so it uses a bidirectional recurrent neural network. A lot of tricks used, dropouts and things like that are fairly standard for these kind of learning. When you look at something like Lubum, you see it does actually a pretty good job of learning. For the scientist data set, it took longer. Now, what was done for the actual evaluation, the primary evaluation, was generate the correct Lubum set. Then we need some ground truth about something that's wrong. So you add some facts that are incorrect. Now, incorrect things in a reasoning system can be things which propagate because there are inferences off of them, and things that can't. And so the paper has some discussion of this that I'm not going to go into. But essentially, things that propagate are where the interesting problem is, right? So if if somebody's a grad student, they have a particular university. So basically what you're comparing to here is how our system does to Jenna for various things. So for the noisy set, right, those things where our correct inferences are defined by Jenna, so Jenna gets 100%, so that's the GCC, right? The other two are cases where noise has been introduced. In one case, the noise has been introduced in such a way that, by definition, you won't get the inferences, and the other one, by definition, you will. So what you see is that essentially the important thing here is the green line. So for RATA, which is the one we're mainly talking about one particular inference, you see it did almost as well as Jenna. For the other one, it did much better because, again, this is where Jenna was propagating the noise and this system wasn't. On the scientist data set, it's much harder to explain because you don't actually know what's correct and incorrect in there for everything. But just an example, I mentioned 1,761 errors of those that are in all of DBpedia. 94 of those fall into this data set. One of the incorrect inferences is that people are agents. So in 6 of the 94, only in 6 of the cases did our inferencer make that assumption. Now, of course, that would be easy to say. If it never made any assumptions, then by definition we would never make any of the wrong ones. So looking at all the things that could be inferred, of the 94, there were 38 where it got exactly the inferences you would expect if you eliminated the fact it was a person. Some of them had inferred properties that Jenna couldn't make, and those were really the most interesting case and makes it, is somewhat leads to some of the future inference. So, for example, this is one of my favorite ones. So Big Ben shows up in there, and Big Ben was both said to be a person and a place. The system, so Jenna, of course, would make it an agent. Our system did not make it an agent, but added that it was a historic place, right? It looked like it had a lot of the same properties, a lot of other things that were historic places. Now, how do you evaluate whether that's correct or not? Because it's not directly asserted that it's a historic place. So some of the inferencing, is, so when you do it in these very large real-world sets, exactly what to measure is not easy. But you see a lot of interesting things. So essentially, we've really shown that you can get out of a learning system an RDFS reasoner that is more noise tolerant than a traditional reasoner. Still not perfect, long way to go. There was a lot of work that I didn't talk about, given the time, about what sort of noise and noise tolerance and what a lot of that means. I showed you very briefly in hand-wavy the layered graph model and the graph words for how we encode the RDF. And again, the details are all in the journal paper. So you can see it. And again, as I said it right at the beginning, all of the code, models, examples, et cetera, are available. Where are we going with this? Well, so one real issue, obviously, is generality. So in theory, I can take my description logic system, put in any set of facts, and get a set of inferences out without, by definition. The good thing about it is I don't have any domain changes. Here, of course, depending on how many things you have, how they do it, how you train, et cetera, you don't get that same kind of generality. So there's a trade-off there. Bassem is now at IBM Research, where he's actually looking at could transfer learning solve some of these problems. And then something that we're looking at together is one of the nice things about the learning actually being able to find and or eliminate the different RDF statements is that you have provenance with those statements. So now you can say, who asserted the thing that was wrong, right? So the system decided that Big Ben was not a person. Can it actually say, hey, this is where that, in Wikipedia who did that, or in some other system. So you can start actually looking at some of the trust stuff. And I will basically stop there. I'll answer whatever questions I can. Those I cannot, you can send to Bassem.
Okay, thank you very much.
Thank you.
We have time for maybe one or two quick questions.
Thank you. Can you comment on whether, say, subproperty reasoning or domain range reasoning or subclass reasoning, which one is better, or how it's of parsing?
Yeah. So the fast answer is if you just take the general RDFS rules and just train it directly, so no noise, right, it will get to, I forget the exact number, it's in the paper, but high 90s% correctness, right? So it's essentially doing a fine job on all of the standard inferencing, caveats, a reasonable size set, a lot of time, all the usual learning things, okay? Interestingly, but when you add noise, again, the different kind of noise, so for example, properties, subproperties, things like that, propagate noise differently than class, subclass, et cetera. So that's what that stuff I kind of hand-waved about the propagation. And then I'm getting, what we sort of showed is that it does a good job of cutting off the ones that, so given something that's asserted with multiple properties, right, if some of those properties start not to look right, they just get cut off. And again, that can be on the, most of these were in the class hierarchy inferences. You get the same thing in property, but for example, in DBpedia, you have very few, you don't have any long sub-property inferences, things like that. So again, it was pretty carefully controlled for the actual paper. And does pretty well, but was not tested on all different types.
Okay, thanks. Very quick one.
Just now, when you were talking about corruptions of the triples, you mentioned some can be propagated, but some cannot be. Can you talk a bit more on why certain things can be propagated and others cannot be?
So again, it depends what kind of inferences come off of the noise that you add. So if you are a grad student who has an advisor, I simply assert that you are not a grad student, or I simply leave that out. There is no advisor inference if all grad students have advisors and you're not grad students, so that doesn't propagate, right? If I say you're at a certain university, then that implies, if I say you are a grad student and an undergraduate, then you end up with an advisor and I forget the exact details. Jeff?
Yeah, thanks. Maybe we could take the questions offline.
So it's all defined in the paper if you look at it. But again, some of these things, when you make a wrong assertion, all it does is remove inferences. So nothing propagates, right? Others of these, when you put them in, you end up with propagation. And there's even somewhere if you take them out, you can get some propagation, but that's a pretty rare category. So that's all in the journal paper, how those work.
Very interesting work. Thank you.
Thank you. And again, he gets all the credit, and please, contact him, ask any technical questions. Feel free.
Okay, that's all for today's session. Thank you all the speakers. Thank you.